Hello everyone. Today I will be sharing my project discussing optimal design and analysis of a closed cycle OTEC system. My name is Justin Quinn. I'm a mechanical engineering student and this is for thermal system design where our instructor is Dr. Lee. Now we're going to get into a little bit of a background and introduction of our project. The aim of this project was to analyze the efficiency and record the data of an ocean thermal energy conversion or OTEC system. We began by evaluating its thermodynamic properties across the certain components that are listed: the evaporator, condenser, turbine, and the pump. We wrote code into MATLAB to help us analyze this data. In the end, the analysis revealed that the system operates more efficiently in terms of energy production. However, it did not lead to complete optimization due to the high net power output. A little more background information on the OTEC system. Given From this figure given in the project details, we can analyze the four processes on the graph, beginning with process 1 to 2. Process 1 to 2 on the graph is showing that the turbine is receiving vapor from the evaporator. Next, we can look at process 2 to 3, where it shows the condenser pressurizing the vapor back into a working fluid. We can also look at process 3 to 4, where the pump is transporting the working fluid, and all the way back from process 4 to 1, where the cycle is restarting through the evaporator. This is the closed system and the process it follows in a linear path. So how can we conclude that an OTEC system is efficient? Well, in order to achieve success, an OTEC system must incorporate a closed system that operates on the Rankine cycle. The fundamental reason for this is that it requires less energy to pressurize a liquid and recover that expanded vapor with the same amount. The Rankine cycle's closed system design offers several benefits, such as a more compact system, reduced environmental impact in terms of space, materials, and waste, and a higher overall efficiency than other systems. By utilizing a closed system, the OTEC system can operate more effectively with a reduced environmental footprint and lower the energy costs to those that use it. Here we can look at some theoretical background and mathematical equations used to find the efficiency of this system. First process, we're in the evaporator stage. It can be balanced using equation 1, which is also known as the first law equation. We then move on to equation 2, which can approximate the thermal conductance of the evaporator. Moving on to process 2 to 3, we then balance the energy. The first law equation must be applied to the condenser, which yields the equations below, with equation 3 and 4. Moving to processes 3 to 4, we can see that the pump consuming the power during the transportation process is shown. Equation 5 shows the value of the working fluid value, and equation 6 shows the required horsepower required for this process. Moving on to equation 7, the gross power output is shown. This represents the working fluid turning into vapor due to pressure and temperature difference under the circumstance that the working fluid's temperature and exit pressure equals the condensation's temperature and that of the saturated pressure. Now we can look at some of the data and the results we found using MATLAB to record the data we entered into our code. The interpolated values of the thermodynamic properties range from 24 degrees Celsius to 22 degrees Celsius in 0.05 degrees increments. Using the MATLAB table and the temperature values we have, the parameters were calculated for when it was at 8.6 degrees Celsius and 8 degrees Celsius. These parameters were then plotted on the MATLAB graphs, which you can see on the next slide, with respect to the warm seawater temperatures ranging from 24 degrees Celsius to 22 degrees Celsius, with a direct comparison of the temperatures mentioned earlier of 8.6 degrees Celsius and 8 degrees Celsius. Now we can visually see this data on the graph shown using MATLAB. Again, the values range from 22 to 24 degrees Celsius and compared that to the 8 to 8.6 degrees Celsius. You can see the graphs have a negative trend, and the graphs are compared to show more efficiency of the OTEC system at 8.6 degrees Celsius. This is because there is more net power and smaller max effective thermal conditions in this scenario. Using the equations we discussed prior, we created these graphs in MATLAB. Again, the values range from 22 degrees to 24 degrees and 8 degrees to 8.6 degrees Celsius. These graphs again, but in a positive trend, show that the 8.6 degrees Celsius system is the most efficient of the two. On the graph shown below, again, the values range from 22 degrees to 24 degrees Celsius and compared to that of the 8 degrees Celsius to 8.6 degrees Celsius. These graphs show work compared to temperature. The following graphs were then compared and showed that, again, the 8.6 degrees Celsius system was more efficient because there is more net power and the smaller max effective thermal conditions applied onto the system. Here we can see our last set of graphs that we plotted in MATLAB. For this calculation, we use parameters of various temperatures ranging from 8 degrees Celsius to 12 degrees Celsius in 0.5 degree increments. We assumed an isentropic efficiency of 0.8. We then calculated the values. They were formed in a table and plotted on these graphs, as you can see. The following graphs show the calculated values of the parameters with respect to cold seawater temperatures as well as the direct comparison between the changes of the temperatures. So what does all this data mean? Well, we can conclude that the OTEC system in a closed ranking cycle is more functional at that temperature 8.6 degrees Celsius. This is due to having a larger net power and smaller max effective thermal condition than the 8 degrees Celsius system. At a constant isentropic efficiency, the system was efficient, but due to the high net power, we can say that it is not the most optimal. Some recommendations for optimizing this efficiency of the steam turbine can be stated by incorporating solar energy to increase the temperature difference in the water, which will result in a higher work output. Next, it could be maintenance on the steam turbines themselves. Any deficiency in the turbine's functionality could result in a loss of efficiency and power output of the turbine. Lastly, we could say that an addition of thermal insulation could avoid any heat loss or gain, or just improve the overall efficiency of these turbines. As said before, we did find the system to be efficient, but not the most optimal. That concludes my presentation. Thank you for taking the time to listen to me, and if you have any questions, please feel free to forward them to my email.